Welcome everyone to this next episode of Iron Riddle, the show where we looked at this awesome, exciting database for financial transactions called Riddle and try to understand how to build something like that. So let's get started. And let's start with a short recap of what we've been up to lately. We've been discussing the storage aspects of Riddle. So Riddle is a replicated state machine, which, as our founder Joran likes to say, makes most sense if you read it backward. It's a machine with a state which is replicated. So we covered the replicated bits when we were discussing consensus. We kind of like glossed over the machine parts, which is just double entry accounting, which is like relatively simple specific rules for how you process financial transactions. And now we are looking at the state part. How the data about transfers and about accounts is stored and is persisted across the time. How is it possible that our database does some things, then say crashes, then restarts, and still is able to provide all our data? And we are looking at the structure of our data file. We mostly look at the static structure, so we are not really thinking about like how data evolves over time. We are looking at a snapshot of a data at a given point in time. So what do we see in our disk on the machine which is running Riddle? Well, we see a single file called a data file, which stores all the data of Riddle. Inside this data file, there is like several regions, several zones, it's really called. We'll discuss some of them. So there's like super block, and we haven't looked at that yet. Then there is a write-ahead log, which is used by consensus to store messages which are received over the network. And but those are actually like relatively tiny, like really small. So superblock is tiny. Write-ahead log is also, well, it is slightly bigger, but it is also relatively tiny. The bulk of the data file is occupied by the grid, and grid is really large. Grid can be like gigabytes. And well, it is called the grid because it divides the rest of the data file into this nice, evenly sized data blocks. So I'm not super great at, dividing things into like even chunks, but this is basically a block. And the block is 5112 kilobytes of data. Okay, so let's actually do this. Okay, a block. Okay, so and this grid structure is like the atomic structure of all our storage. So the smallest amount of data you can write or read from terabit storage internally is a single block, is 512 KBs. So last time we looked at how the write path works. Like how do we write a single block of data? That's actually it's like super simple code because, well, the start offset of a grid in a data file is just some compile time constant, and then a specific offset inside the grid is just, well, the start offset plus the index of the block multiplied by the block size. Actually, let me just show this code. TB iron beetle. Okay, let's go to the grid, let's go to the right block, and here we should, yeah, we have this block offset function. Like block offset function is like super simple. It's just block size multiplied by address, and the offset of the grid itself is edited internally by the storage. So here we pass this dot grid zone, and here we offset inside the zone, which takes the start offset of the zone, and that's like logical offset of a single block inside the grid. Okay, so that's stupid easy. Today we are going to look at the read path for the grid. Now that we have written some blocks to the grid, how we can actually read them back. And last time I left you with the puzzle. So coming back to the LSM tree, when like to kind of like again a little bit of a how do you call it, practice. What we use grid for specifically is for storing LSM tree. So LSM tree is organized as a set of tables specifically as a sequence of layers of tables, and each table is an index block and a bunch of value blocks. Value blocks store sorted array of values, index blocks point to value blocks. So when we read something from a tree, we essentially binary search inside each layer for a particular table which contains this value, and then we binary search inside a table, which means that we binary search for the data block, and then we binary search inside of the data block. So somewhere there we obviously need to have a code for reading the actual blocks from disk. So we need to read the, once we identified the table, we need to read the index block, and after we've binary searched inside the index block, we need to read the data block. And you see we have like those two functions here, read index block, read data block. And here is the puzzle. If you, of course, like this read operations are synchronous, but if you look at the signature of callbacks, then those callbacks accept just a pointer to the index block. And it looks like, there is no error handling here. So we just like read something, and then we get whatever we were intended to read without any kind of errors, and then we continue using it. The same goes for a data block. Like we want to read like this. Where, like, read data block. Okay. Oh, right, yeah. So, okay, we want to find some value. We go and read index block. In the callback for index block, we gather our index block, then we binary search for the value block, and then we go and read this specific value block from the grid. So we pass this address and the checksum, and then once we read the data block, we go and binary search inside this data block. And again, there's absolutely zero error handling here. We read something from disk and we just get this data and we binary search it. And this should be very surprising because, as I've said many times, one of the distinguishing features of TigerBiddle is that TigerBiddle has storage fault model. That means that we don't assume that disk works correctly. We assume that disk can return an error, or maybe even sometimes disk can outright return a wrong data. So you do a write call from a disk, you get some bytes back, but the bytes are actually invalid, they are incorrect. And presumably, somehow, TigerBiddle deals with all these kinds of issues and keeps your data safe. But here we see that we read something from disk and we seems to ignore the error. There's no error hiding here. So what happens? Maybe we unwrap and panic somewhere on error, or maybe just drop the error on the floor and pretend that it doesn't happen. What gives? Well, let's go and take a look what happens here. Let's do this code for reading the data block. Okay, so first looking at the call side, we pass our callback. We pass our context as usual. For any time you schedule an asynchronous separation TigerBiddle, you need to have some kind of a statically allocated context object, and you pass the address and the checksum of a block you want to read. That seems pretty self-explanatory. One thing we need to keep in mind is that we curiously we don't pass callback like this. We don't pass callback like this. Rather, they pass some kind of enum, and this is curious because this callback kind of you can pass two kinds of callbacks from local storage and from local or global storage, and that is actually the answer to this question. So what happens here is that TigerBiddle can transparently read a particular data block either from its local disk or from some of remote replicas. And sorry if I'm hitting my microphone with my head and that makes some terrible noises. I will try to avoid that in the future. Okay, so that means that if we try to read something from our disk and it is not there, or it is there but corrupted, we transparently go and read something from a remote replica, which is, a synchronous operation. It doesn't really matter whether bytes come from disk or from network. From the caller perspective, it's still the same. You schedule some callback, and then later you get your data back. And that's why grid encapsulates this remote repair and provides an API where nothing ever fails, because if something fails, we go and read the same data from a different replica. You might say, okay, Alexei, but what happens if this read actually happens on every single replica? What if, for example, the data gets corrupted everywhere? Well, in this case, any single replica will become stuck. It won't have like any data block to read, and that is actually correct behavior, because if some portion of data became completely unavailable because it got corrupted on every single disk on every single replica, well, then the correct behavior of a cluster is to stop accepting transactions to get stuck. Because, well, it cannot access the data which was stored before, so state transitions are not necessarily valid. But again, of course, in the all but the most extreme cases, we actually expect that some replica will have a copy of this data and will be able to transparently read it. Okay, so let's dive in and understand how this read block works. Okay, so we are in from local or global storage case. Read block. Yeah, from local or global storage case. It is exactly the case where we allow transparent recovery using remote replicas. Okay, so let's go and look there. I think we passed cache read, so let's look at the code path where we go through cache. And actually, because kind of like we haven't covered this yet. Probably we won't cover the cache today completely, but basically grid also transparently caches block, and when calling code invokes separation, it might be the case that the block is cached or is uncached. And those operations differ in their synchronity. In the cached case, you can get the block immediately. In the uncached case, well, it's going to, like, your callback is going to happen on some future iteration on event loop. But one rule when you do asynchronous programming is that your API should always be asynchronous or should always be synchronous. So in this case, and that is important to like avoid issues like stack overflows, because again, so here like we potentially block is uncached, and potentially we can invoke this callback immediately. But if that happens, we invoke a callback when there is something else on the stack before it, and if that callback invokes some other callback which also happens to invoke to be invoked sequentially, we'll get and eventually overflow the stack. So that's why we call this on the next tick, so that when we get to invoking this callback, nothing else is above it on the stack. So in terms of do we have? Yeah, so in terms of like what's going to be on the stack, by the time we invoke this red block tick callback, it's going just to be like this code. So our core run loop for IO urine. Okay, so there. We do this, hey, check if the read is already processing, recovering, and merge with it, which is actually part of that transparent remote recovery procedure. But let's actually kind of like follow the code as it's going to be executed, and folding in VS Code is still completely abysmal. Like, I mean, like, why can't you do the right thing? Like, I want you to fold this block. It's completely useless. Sorry about that. Hopefully the Z editor soon will be supported on Linux, and I will be able to use proper editor here rather than this joke of a browser. Anyway, here's the real part. Cache read. As a reminder, we do pass cache read here. So we say, yeah, agreed, this block is likely in cache, so please check the cache. Okay. So if we are able to I'll read the block from, well, actually, let's kind of like pick at the very top of our like cache infrastructure. So we want to read block from cache using address and checksum. As usual, there is like a whole bunch of assertions. Then we go to the index, to the cache, and say, okay, cache, what is the index for this address? And cache internally is just one big array. Then we get the block. And if the block is the block we're looking for, and well, why might it be a different block? Well, because it's a cache. Cache is smaller than a grid. So multiple different blocks might actually happen to occupy the same address. So kind of like the block we are looking for, if it is in the cache, it should be at the index, but well, maybe there is a conflict with some other blocks. So that's why it's not a cache, and that's why you kind of like need to verify the checksum. So if the checksum is the same, we go and resolve, we go and return this cache block, and then we go and resolve read. So let's not look at the resolve, the block resolve function right now, but well, we already understand that what it would do is that it would call our callback with this cache block that we had. Okay, let's follow along. Let's say that, hey, we didn't actually get a cache hit here. What would we do then? Well, we enqueue our read in the queue of blocks that need to get read. Why we need a queue here? Well, as usual, everything in Tybidal is limited. So grid maintains an array of IOPS. So there is like only read IOPS match blocks that the grid can be written at the same time simultaneously. So there might only be read IOPS max outstanding read syscalls in the kernel. And in general, yeah, we kind of like can ask the grid to read more than that. So if it does not have a free IOP, it needs to enqueue the read. And again, this is the same kind of intrusive linked list which we looked at last time. So, okay, if we actually, like the way this works is that we always enqueue. So there's like always a queue of reads which needs to be in execution, and after we enqueue, we try to acquire an IOP and start some previous enqueued read to work. And that's actually like the helpful comment why we do this, rather than, you know, like doing something like this, like try read immediately and enqueue only in the other case. This is because we want to maintain fairness. We want to say if we first enqueued read A and then read B, then we want read A to start executing first rather than read B. So yeah, that's why we always enqueue in the end. Then we try to acquire IOP. And if we did acquire IOP, we actually start a read operation from our storage. So here we go and say to our dear storage, please read me this. Okay, yeah. So so here we normally pass like some buffer, like where to read. So this is like buffer. Here we pass IO block, and this is a statically allocated array of blocks where we do the reads. So this thing here is the syscalls, so just the asynchronous operations themselves, and this here buffers for storing the actual data. So this essentially is like half a megabyte pointer to a particular block. We ask storage to read from the grid zone and compute the offset from a block address by multiplying the address by what? By the size of the block. Okay, then once we've done, this is where it gets interesting, because this like operation read sectors can actually fail. Like we might get data with the wrong checksum due to some error on our read, so we need to deal with it here. And let's look how this happens. So like first of all, there is like some cancellation stuff, and we do have cancellation. And at some point, I will explain how cancellation works and why we need it for. But for now, kind of like let's ignore this again. Kind of like we'll be building this onion of a database like one layer at a time. Hopefully, we won't be crying too much. Okay. Then. Okay. Yeah. Then we insert our block in the cache if the caller asked us to actually cache this block. So you see, when we read the block from disk, we pass two cache parameters, whether it makes sense to try to look up this block in the cache, and whether it makes sense to add this block to the cache later. Because well, for normal operations, of course, you want to cache blocks. But for example, if the read comes from a repair request, so some replica somewhere realizes that one of its blocks is broken and it wants to repair it, well, that replica needs this block, but you probably won't need this block again, so you can say, hey, I don't want to cache it. But anyway, if we do cache it, then we figure out the index where we should insert this thing, insert our block in the cache. Well, okay, so this is kind of like super weird API, because grid always deals with pointers to block. So a block is a pointer to data, and we deal with pointers to pointers. And that is exactly for like this mem swap operation. So when here we pass wait, do we actually pass? No, we don't pass. Okay, I'm confused here, but okay, yeah, I think this happens on the right path. So on the right path, when you well, actually, let's look this up here. When you write a block, you pass a pointer to a pointer, and that means that when the grid tries to block, rather than just like writing this data, it just puts this data in the cache and overwrites your pointer. So grid gives you back some free pointer from the cache, and I think that's like roughly what is happening here, or maybe not. Maybe I'm confused. Okay. Yeah. Okay. So basically, probably we'll need to take a closer look here in an episode dedicated specifically for how the cache works, and hopefully by that time we write the cache so there is no this like 2-star shenanigans. We should like 1 star more than I can understand. But anyway, kind of like the idea here is that we like if we need to insert this block in the cache, we also insert this block in the cache, and then we get our block. Then Well, actually, it's okay. So okay, now I stopped understanding something, because we should be like, this is the layer where we need to have error handling, because like we need to check the checksum. Read block validate. Okay, so here. Okay, this is very curious. So yes, we read something from the storage. That thing, if you recall, our underlying storage API doesn't return errors, because one of the error that we could have is that the data is just invalid. Like our disk returns some garbage without signaling about this. So even if our read syscalls returns an error, we don't report that to the caller, and we just set the underlying data to 0, because the caller should be validating the checksums anyway. And read block validate is what will be handling this validation. But I'm surprised that we actually insert stuff in the cache before we do validation. But well, apparently, if the validation didn't succeed, then we will evict this block from the cache later, which is again, cache is like tricky code. Okay. Anyway, so insert potentially invalid block in the cache. Then, this is interesting. This is. Oh no! This is actually not a super interesting code. So okay, we finished the read. So now our IOP is free, and we might start a different read. So we go, and if we have some other pending reads, then we pop a next read from the queue of pending reads, and we again start this disk access operation. If we don't have any pending reads right now, well, we release our IOP to the pool of free IOP, so that the next time we start a read and try to acquire IOP here, we actually, well, get an IOP and can start a read immediately. Okay. Then we okay, so this is something I'm slightly confused about. So we okay, so probably we have like two queues of reads. Read queue is everything that is scheduled to be read. So like all in progress read, which are kind of like logically in progress. And some of those reads are actually executing on the hard drive. So there is a syscall that we issued to read the data. And some of those reads are waiting for a read IOP to be available. So for a syscall slot to be available. And again, like the syscall slot is not like, a physical limit in the operating system which says, hey, you can do like only 10 syscalls or something like that. No, it is just our like logical limit that we don't want to do like more than 10 syscalls at the same time. Okay, and those reads who wait for an available IOP, they are in this read pending, which is a subset of a read queue. Okay, so we are always in read queue, so we go and remove ourselves from that list. Then we do the actual block validation. The thing which might say, hey, whether this underlying disk operation succeeded or failed. So again, as usual, cast the prefix of our data block to the header, because every bit of data in target bit starts with the header, and then we validate the checksum of the header itself. Well, if it is not valid, then we return invalid checksum, and we are done. Then we validate a command thing, which says like what is stored there. And well, we expect to see a block there. But again, if we get a misdirected write from our write ahead log into the grid, we might actually see a prepare here. Or I think we also store client reply, so this also might be a reply. But anyway, that would be a case of a misdirected read. And that's why it could also be like an expected command. Then we validate that like the entire block is valid. So here we only checked the header, like the small part of the block. Here we check like the entire block. Then we check that, hey, this is actually the correct block. So not only checksum is self-consistent, it is also the checksum which we are looking for. This is very important because one of the failure modes of disks are misdirected operations, where you get correct data from disk, but from the wrong offset. You ask disk to read something from the offset 1000, and it says to you, hey, here is your block you asked to read me from the offset 2000. And well, if you look only at the validity of internal checksum, you miss the failure mode. So you need to always double check the checksum against something external. And this is exactly what we are doing here. And well, if all those checks, well, if the checksum matched, then the address must match as well, unless we have some bug in our code, and then we return valid. Okay, so we after validating this block, we got a result which might or might not be valid. If it is not valid, then we remove it from the cache and log it. And then we call read block resolve with result. So read block resolve might actually needs to deal with potentially invalid blocks. So let me double check that when we hit the cache, we actually called this with a valid. Okay. Read block. So let me see here. Yeah, when we serviced the block from the cache, we call read resolve from valid. Okay, so let's get closer to the mystery. Let's see how we deal with valid and invalid blocks here. Okay, so there is like some extra checks for validity if the read is coherent, and coherency is something what we'll get to once we'll be discussing checkpoints. Some more validation. Then again, like the interesting code, which we'll cover a little bit later. Or maybe, okay, let's let's do this here. So each read in a grid stores the set of I'm wondering. Okay, so that's a bit tricky. I kind of don't fully have this in the cache, so you have to understand this with me. But basically, the idea here is that each read stores a queue of reads which are trying to read the same block. So if a single read succeeded, that might actually mean that the result of this read could work for a number of different reads. And if that happens, then for each of those reads which are for the same block, if we read a valid block, then we just go and call the callback for that read. So we kind of immediately say, hey, that read is now done. And I think, okay, so let's keep these on the left side, and here let's get back to that bit of code that we have skipped. Yeah. So this is how we kind of like retire resolved read, and here how we populate it. So we, for the queue of existing reads, if we found a queued read for the same checksum, then we add our current read to the set of reads that read would resolve. Yes, and I was missing this return. And if we edit our read to another read to be resolved, then we return. So kind of like when you try to read something from grid, basically there are two cases. First, you're like the first one who reads this block, so you go and read it. But if there is someone else who is already reading this block, you are not going to read it again. Rather, you are just going to enqueue to the end of that other read, so that when that read completes, it also invokes your own callback. Okay, so, but that happens only if the result is valid, if we read the block and the checksum matches. If the checksum didn't match, then we add this to queue of reads which must be resolved using remote storage. And then we finally invoke our own callback. And our own callback, if you recall from the very beginning, was from local or global storage. So we allow this, we want to opt into this transparent repairing thing. So if result is valid, then we invoke the callback. Otherwise, we enqueue our reads to those remote reads as well. So what do we do with these remote reads? This is kind of the answer to the question how this like transparent remote repair gets triggered. Well, if this is not empty, then we take the first one. What is this? Read, pending, read. Well, I kind of lost it here. Oh, right, because resolves is not a queue of reads. Resolves is the queue of reads. Well, okay, because read participates in two orthogonal, might participate in two orthogonal queues at the same time. It participates in the queue of reads which is stored on the grid, but it also participates in this like pending queue. And you cannot do this, make this a FIFO of read, because well, those two different FIFOs which will be used at the same time are going to conflict for this next field. So that's why we actually have two next fields here. One is in the read pending, and read pending is just linked list. So again, this is not something related to the database, it's just something related to systems programming and intrusive connections. Okay, anyway, kind of like we got our okay, so origin remote resolves is actually a linked list. It's already a FIFO, so is it a FIFO? Yeah, it's already a FIFO. And this is kind of like our local FIFO for what's problematic with this particular read. And on the replica, we have this global FIFO of reads that need to be solved by remote repair. So what we want to do here is we want to append this local read, like this local queue with this global queue. And yes, so here we FIFO. Oh, okay. So it's hard to. It would be extremely hard to explain to us C why this code is valid because we have like this crazy circular linked list. But okay, so I kind of like understand this code. I don't think I understand it to a sufficient degree so that I'm able to explain it. But just like kind of like logically, what we do is that we append this queue to this queue. And we also append the block to a fixed size queue of missing blocks. So how? Okay, I'm wondering, will we? Oh, we should be able to cover remote repair. So bottom line is that global queue, yeah. Our read might fail, and in that case, we don't invoke the callback with some kind of like, hey, your read didn't succeed. No, rather we enqueue this read in like the global queue of reads which need to be repaired, and we enqueue the block from this read into this blocks missing data structure. So let's look at blocks missing. It should be relatively simple, I hope. Well, no, it also, well, I made it's also deals with repairing the whole tables, which likely we won't get to today. Basically, from this entire grid blocks missing data structure, we only will be using like these faulty blocks, which is just an array list of a fixed size of faulty blocks, where faulty block is its checksum, its address, and the address is the key, and its state, like where this block is waiting to get fetched, where it is writing to disk, or where it is aborted. Okay, so let's look how we actually then drive the repair. And that happens, I think that happens in replica. So blocks missing. The core thing here is that, well, we have blocks missing, which records the set of blocks we want to repair. And replica well, I'm not seeing here. Oh, let me see. I think that the request, which the replica is called block. Yeah. Oh, it's called request block, I think. Request block. Request blocks. And how do we determine which blocks are we sending? Okay, yeah. So in the grid, we have this next batch of block requests method, which like communicates to the caller which blocks are currently waiting for the repair. So the caller processes the buffer, and the grid goes and okay, that needs a close loop. Okay, so replica asked the grid which blocks need to be repaired. We go through all our reads, which are like which failed locally and which are queued to be on remote. And we enqueue the read from that remote. And here I'm actually curious. Do we have an invariant here so that all like globally queued reads are for distinct blocks basically? Could it be the case that we get identical blocks here? Because I don't necessarily see that. Well, we are not checking this this invariant locally, and it feels like it could be violated. Okay, so those all are for the same block address. Okay, yeah, so actually we enqueue only a single read to the global queue, and that read contains all the other reads in its resolves queue. So kind of like it's two-dimensional queue, two-dimensional linked list. Well, I like to say that like systems programming is like easy because like every like 90% of what you do in systems programming is like you take number and like multiply by another number and add a number to get the offset, or like you take a number and then you take it more some other number, and that's easy. The remaining 10% of systems programming is linked lists, and linked lists are hard. Okay, so coming back to reading blocks, I think that's actually yeah. Let's actually stop at that because I think blocks missing. It sounds like it might actually include duplicate blocks here, like because like we like push read in the read global queue. And we also enqueue this into blocks missing queue. And here, well, we first go through, again, read global queue, but then we also go through the blocks missing. So it feels like we might be including the same block a couple of times, which wouldn't be a correctness issue, but it would be, well, waste performance because, well, you could have included different blocks, I think. Okay, anyway, so going back to replica, next batch of block requests. So replica now gets blocks to be repaired from the grid, and then sends a requests to any other replica. And if you trace back this request is just a body part of our message. And again, we actually never check that there aren't any duplicates here, which feels redundant. Okay, and when do we send request block? I think that happens just on a timeout. Yeah, so basically on grid repair message timeout. So periodically, replica goes and sends these requests. Actually, wonder if we perhaps should be calling this a little more frequently. Yeah, kind of like it. Yeah, it would be nice if we actually we were able to say on tick that, hey, if we have anything we want to repair, then we go and repair it on the next tick rather than waiting for a timeout. But like whatever. Okay, so we send request blocks. Well, let's see the like other side of it. On request blocks, we go and see whether we are already reading this. And well, if we are already reading this and we like cannot solve this, or we like ignore this request. If we are not reading this, we are trying to acquire a grid read because we only want to use spare reads for this functionality. And if we fail to acquire a read, then we return rather than continue because, well, we won't be able to read anything else. And then we ask the grid to read the block. And this time we only ask grid to read this block from local storage, so that as not to like amplify this across the entire cluster. And we ask it to cache our read, but do not cache write. Well, yeah, it's like in Target we have this weird beginning naming convention where like we say foo bar, but like bar foo, so that like like also where it's so kind of like we don't say like address of the block, address of the checksum of the block. We say like block address, block checksum. So here, like the way you read like cache read and cache write, like cache is actually the noun and read is a verb. So read from cache and write to cache. And but sadly in this case, cache write reads as if cache is a verb, and whether it asks like whether we need to cache write. This is just completely wrong. No, this asks whether we should update the cache. I think this cache update would have the same problem. Naming is hard, even if you do begin in tag style naming. Anyway, so we ask the grid to read this block, and if we have successfully read this block, and well, because this is like the local result here, we actually get a result, so it might be invalid. So if it is valid, then we send this block directly as a message to replica. And this is cool. Again, I underscored many times that at Target we kind of have the single message, and message is what you get on the network and what you write to disk and what you read from disk. And this is great because we read something from disk and we send this immediately to the caller as is without. Well, we do have this memcopy here, but this is because the cache works in this confusing way with like double point everything like this. That there shouldn't actually be any memcopy here. We should be able to send this message as is right to the network. Anyway, so what we're sending is we're sending the block. So let's see. Then we are back to the replica, which tries to repair, and it receives a block. And on block, it calls, well, fulfill. Oh, do we? Oh, right. So, what does replica need to do when it receives a block, presumably as a response to a repair message? Well, it needs to do two things. First, it needs to resolve any pending reads, because remember, a read which failed locally isn't like immediately retired. The callback isn't called, rather it isn't queued. So we need to like call all those pending callbacks. And then we need to actually go and write this block to disk. So first we fulfill the block, which goes through all the reads which are pending. And if the read happens to be for the same block, we call read block resolve. And this time we call it with a valid block, so we like invoke all the callbacks. And then if we are waiting for this block, okay, so it seems I might have misunderstood the code. It seems like the set of blocks between blocks missing and blocks in read pending might actually be like not necessarily, one might not necessarily be the subset of the other, so they might be more in relation. So anyway, kind of like we separately decide whether we should resolve any pending reads and whether we should add this block to repair. Actually, resolve. Yeah, it's well, okay, yeah. So it's that's kind of like subtle. Everything in Target is limited, so there is only finite number of blocks we might be repairing through blocks missing, and well, it might be the case that we actually haven't enqueued block here. So even though we got the block and resolved the read, we might still not repair it on our local rig, which is still going to be fine because we will repair this block at some point later because we have a grid scrubber which periodically reads everything and repairs any latent failures. But still, that's kind of like an interesting thing. Okay, so if we are actually wanting to repair this block, and if we have a spare grid write, then we go and repair this block. And that writes this block, and what is the callback here? Repair block. Grid block repair callback. Well, okay, so that's like, okay, so that is confusing, and that's not something I'm going to discuss today, but why this infrastructure looks slightly more complicated than it is because besides the case where we need to repair something because something is broken on disk, like some bits got flipped, there is even a more common case where a replica state syncs. So if some replica is lagging and then rejoins the cluster, it needs to sync the state. And we actually use the same infrastructure for repair and for state sync. Basically, a replica which doesn't have some state because it got corrupted is indistinguishable from a replica which doesn't have some state because it was lagging from the cluster. And in this like repair thing, we also need to check whether we can progress our sync further. So that's why there is like the sync reclaim table, which contains some extra logic, which I'm not going to discuss right now. Okay, but I think that actually kind of like covers this. So And we are like slightly out of time, so let's recap. How grid read workflow works. It is complicated. It is complicated because grid transparently reads data block from other replicas. And like the idea here is that the caller says, hey, read me this block, here is your checksum and here is your address, and the grid might read it from a local disk or it might read it from some other replica, and the caller doesn't know. The caller has like infallible API which always returns correct block with the correct checksum. Internally, grid reads are split into reads from local disk and reads from local disk or global cluster state. And LSM uses reads of a second kind, where we like don't care where this data comes from. When grid tries to serve a read, first it looks in the cache. If it is not in the cache, it adds a read to a queue of reads and tries to start a read using an available input-output iteration, if it is available. If IOP is available, then we go and start a syscall to read data from our local disk. When that syscall finishes, we cache our block, and then we check whether the data is correct, whether the checksum is matches. If the checksum matches, well, we have won. We invoke the callback for the read, and we're done. If the checksum doesn't match, so our local storage doesn't actually have that data. First, well, we remove bad data from the cache. Then we add read to the global queue, well, to the queue of reads which need to be resolved using data files from other replicas. That queue is periodically fetched by the replica. So replica goes through that queue of reads which need remote help, looks at the blocks from that queue, and looks for blocks in that queue, and well, sends a request to random other replica. That other replica does a grid read. This time, this replica reads only from its local storage. If it is not successful, well, it just ignores the request. And the original failing replica will repeat this request against some other replica in the future. And eventually it will find the one which has the block. But if the replica which helps with repair finds this block on its local disk and the checksum matches, well, it goes and sends this block to the original replica. When the original replica receives this block, first it goes and resolves any pending reads for this block, and then it goes and writes this block to disk. So I guess the two big ideas here is that you can read from local disk and from remote replicas transparently, and like you don't need to like make this distinction in the API. The API could be give me the block, and it doesn't matter if the block is from local storage or from remote cluster. So this is cool, and this is actually like the reason why this is cool is that because this removes error handling from your API. On your API level, you just get the correct data always. And this is important because a lot of bugs in real-world software come from error handling, because error handling code is very tricky. Error handling code is rarely exercised, and that's why it is always buggy. So if you are able to define away error handling code, that is always a win. And here we did refactor this away. There is no error handling in the tree. Again, coming back, like why this whole shebang. when we read something from the grid, well, we just use the log. We don't even validate the checksum because we know that it must be correct. The second important thing, which kind of like was implicit, but if you kind of like carefully look into every line of code, you see that this concern is like threaded throughout, is that always, at any time, whenever you read something from disk, you already know the checksum. So you first got the checksum from somewhere, and then using this checksum, you drive everything else. So in particular, I guess, like, on request blocks, you see that we just go and take the checksum from the request address. So again, replica doesn't ask like, hey, give me a block at the address 92. It always like the address and the checksum. And internally, when the LSM tree asks the grid to read the block, it's always also the address and the checksum. With that, I think we are probably done. So here is the answer to the riddle. This is how Tybidal makes reads inflatable. It just transparently reads data either from a local disk or from a cluster and it kind of like tries to do this until it eventually succeeds. This, I think, is all for today. Sorry for like super dense and super packed episode today. Hopefully we'll get more of these episodes in the future because, well, LSM is loads of fun. And join me again in a week at 5 p.m. UTC live on Twitch. And thank you for watching.